this is the corollary, which is very similar to the previous one. In the previous content, the only difference is that here we are going to prove the result for the row rank of the matrix, right? Okay, and the result is, if B is obtained from A by applying the row operations, then row space of A is equal to row space of B, and consequently the row rank of A is equal to the row rank of B, right? So let's start with the proof. Now, since B is obtained from A by applying the row operations, so there exists a non-singular matrix, say P. So therefore there exists a non-singular matrix P such that B is equal to P multiplied with A. Let's take our matrix A to be, that is denoted as Aij, and it is m by n matrix, right? And let me write this matrix further in the row form. So this is R1, R2 up to how many rows are there? M. So writing Rm here. And let this non-singular matrix P be denoted as Pij, and let me take this matrix to be as a square matrix. So this is, let's say, m by m. So the number of rows and columns are same for the non-singular matrix P, right? And then we need to multiply these two matrices. So writing P as, because it is m by m matrix, so I'm writing this as first row, first column, that is P11. First row, second column, that is P12, so on. How many columns are there? M. So this is P1m. Then second row, first column. Second row, second column, so on. Second row, mth column. Likewise, in the last row we get, because the number of rows are m, so it starts with Pm1. Mth row, first column. Mth row, second column, so on. Mth row, mth column. So this is Pmm, right? And this is R1, R2, so on up to Rm. Multiplying these two matrices, we get P11R1 plus P12R2 plus so on P1m into Rm. Then P21R1 plus P22R2 plus so on P2m Rm. Likewise, Pm1R1 plus Pm2R2 plus so on Pm Rm. Now if you notice again over here, these rows of PA are the linear combinations of R1, R2, R3 up to Rm, right? Now because the rows of P are the linear combinations of these rows R1, R2, Rm, so consequently these lie in the row space of A, right? So the rows of PA are linear combinations of R1, R2, R3 up to Rm, so consequently lie in the row space of A, right? So thus row space of PA is a subset of row space of A. Please mark this as 1. Now I need to prove that row space of A is a subset of row space of PA, the other way, right? So again, let's take the row space of A. Can I write this as row space of IA? One and the same thing, right? So where I is the identity matrix. So this further can be written as, because I have taken P to be as a non-singular matrix, so I'm making use of that. So I can be written as P inverse P A. Let me take this product together. So this is row space of P inverse PA, right? Which is the subset of row space of PA. By using the first result, yes, what is the result? If row space of PA is a subset of row space of A, this is the first result, right? Where this P is your m by m matrix. Now here I am having PA with P inverse. Here I am having A with P, right? and P is M by M matrix. Here I'm having PA with P inverse, and this is also your M by M matrix. So by this result I can say that if row space of PA is a subset of row space of A, then row space of P inverse PA is a subset of row space of PA. So this first result has been used over here. So this implies, what is the left hand side? Row space of A. So row space of A is a subset of row space of PA. Please mark this as 2. So from 1 and 2 we get, 1 says that row space of PA is a subset of row space of A, and 2 states that row space of A is a subset of row space of PA. So from 1 and 2 we can say that row space of A is equal to row space of PA, right? Now because these two are equal, so this implies the dimension of row space of A is equal to the dimension of row space of PA, right? And dimension of row space of A is nothing but the row rank of A. So row rank of A is equal to row rank of PA. And because we have stated that if there exists a non-singular matrix P such that this PA is equal to B, we have stated this over here. Yes? If B is obtained from A by row operations, then there exists a non-singular matrix P such that this B is equal to product of P and A. So from here, I am writing this PA to be as B. So this implies row rank of A is equal to row rank of B, because reason PA is equal to B. Hence the result